Hi everybody, welcome to the pre-recorded lecture number two, and let me remind you what we've been doing so far. So far I introduced these numbers called Stirling numbers of the second kind. Right, so we're studying these partitions of a set into set partitions of bracket n into k blocks. So we have some partition A, A1, A2, etc. up to AK. These are all AIs are non-empty and pairwise disjoint sets. Disjoint, and they satisfy that the union of A1, A2, all the way up to AK is equal to bracket n. And so and such objects are called partition of bracket n into k blocks. So, and S of n comma k is the number of such objects, number of partitions, bracket n into k blocks. So I mentioned that the formula for S and k is slightly more complicated than usual, but the recurrence was easy. The recurrence S n comma k is equal to S n minus 1, k minus 1 plus k times S of n minus 1 comma k. And the idea of the proof was you look at your partition and you look at the block which contains the last element n, and then you kind of, if it's a singleton block, then you get this many options, and otherwise you can remove the element and then you still get k blocks, so to which you can add the extra element in k different ways. So first of all, today I'm going to explain a kind of a completely closed formula. Well, it's not really closed. There are going to be some summation formula for S and K. But before that, anyways, there's going to be a few formulas, and some of them are going to be more naturally looking but harder to compute, and some are going to be less nice but easier to compute. So yeah, there is a spectrum of formulas I'm going to prove. So first of all, here is I think a very cool formula which is not exactly super useful. So proposition is that S of n comma k is equal to the sum. I'm taking the sum over all weakly increasing sequences, A1, A2, all the way up to A n minus k. So I'm looking at increasing sequences of n minus k numbers. And then what I'm going to do is I'm just going to multiply. I'm just going to multiply these numbers together. A n minus k. And the claim is that what I'm going to get is these Stirling numbers of the second kind. So let's see if I can look at the table and then maybe do some example. So let's say maybe I want to compute. Should I do this one? 6 or maybe 7? Yeah, let's try 7. So S of 4 comma 2 should be equal to 7. S of 4 comma 2 is equal to, okay, what should I do? I should take, so that's an example, I should take the sum over sequences of length n minus k. So n minus k, n is equal to 4, k is equal to 2, so n minus k is equal to 2. So I'm taking all sequences of length 2, of numbers between 1 and k. So k is 2. Okay, that sounds easy. I can do 1 times 1 plus 1 times 2 plus 2 times 2. And that's 7. Which is nice. That's the same 7 as here. Maybe should I try... yeah, maybe I should try 6. I don't want to try too hard. Yeah, maybe I can even try a harder one. Okay, so which one? Yeah, let's try 15. S of 5, 5, comma 2. So here n minus k is equal to 3. So I'm taking longer sequences. But in each sequence I'm only using 1s and 2s. So 1 times 1 times 1 is 1 times, and they have to be weakly increasing. 1 times 2 times 2 plus 2 times 2 times 2 is 8 plus 4 plus 2 plus 1. Yeah, is that 15? Okay, that's 15. Yeah, so, I mean, it works. But why does it work is completely mysterious. Like, how do you... And actually, I don't even know a bijective proof. I haven't thought about it, but it's really not clear. Like, the right-hand side counts some sort of objects, and the left-hand side counts set partitions, so why are these two equal to each other? And that's another nice trick that we're going to learn. So, the proof, which again, so this idea is used all over the place. And the proof is to just show that both of these, the left-hand side and the right-hand side, satisfy the same recurrence relation. So let me actually copy the statement. Yeah, the idea is that, so okay, let's denote the right hand side, this right hand side here, by h of n comma k. So the goal is to prove that h of nk is equal to s of nk, and the idea is to show that to find a recurrence for h of n comma k. And okay, so what is the thing that we need to show? Want to show the following thing: h of n comma k. Right? That's the same recurrence as the one for s of nk. It's equal to h of n minus 1 comma k minus 1 plus k times h of n minus 1 comma k. Yeah. So how do you do that? How do you you consider the basically you can consider the last term of your sequence. The last term is either equal to k or it's strictly less than k. In the first case is a n minus k is equal to k, and the second case, or yeah, maybe let's say this one is strictly less than k, and the second case is that a n minus k is equal to k. So okay, yeah, I think okay, let me try to fix the notes. So here instead of a k it should be a n minus k. A n minus k. Yeah. Okay. And so if a n minus k is less than k, then so what do we have? We just get that you can replace k here by k minus 1, and you preserve n minus k. So in other words, yeah, this contributes h of n minus 1 comma k minus 1. Right? Again, the length of the sequence is n minus k, which is the same here. So if your last number is strictly less than k, then the same sequence would appear for if we had k minus 1 instead of k. And we would get all sequences this way. And similarly, if this last number is equal to k, then we can just kind of remove it from the sequence, and we get a shorter sequence with the same kind of definition. So, and but it's going to get multiplied by k. So the conclusion is that the sum over all terms for which the last one is equal to k is equal to k times h of n minus 1 comma k. Right, so here I have n minus 1 comma k because the length is going to decrease by 1. And that's why I decrease n but not k. Okay, and so that's it. That's the proof of the recurrence for the h's. And from here, I guess you can find some sort of bijective argument by just recursively bijecting, constructing the bijection recursively. But yeah, in general, especially for things like Catalan numbers, which satisfy recurrence that we're going to study, it's very useful to, if you want, instead of looking for a bijection, just at the level of recurrences to match the two sequences. So yeah, I also need to check, and you have to be careful with that, and that's where collecting tables of numbers is very useful. You have to be careful about the initial conditions. So what are the initial conditions? Yeah, let me write it down. Also need to check the base case of the recurrence. Conditions of the recurrences. And the initial conditions are, so if you look at the triangle, right, the recurrence for the s's, it tells you that you can compute each number in terms of the number above it and the number above to the left. So in particular, if you just specify all these ones here and the ones here, then you can proceed. Okay, if you know this one, then you know the three. So you can kind of proceed row by row to construct all these rows. So essentially, all you need is to check these initial conditions with the ones. And similarly for the h's, because the recurrence proceeds in the same way. So all you need to check is that s of n comma n, s of n comma 1, that's equal to 1, and similarly h of n comma n. So you need to check that h of n comma 1, these are equal to 1. So how do you do that? Well, what is h? H of n comma n it's the sum over sequences of length. So the length has to be n minus k, which is, in this case, it's 0. Well, it's not 0, but it's the empty sequence. Basically, yeah, there is just one, the sum over one object, which is an empty sequence, and the product over an empty set is always 1. Basically, yeah, so it's just, it's equal to 1, because it's the sum over one sequence which is empty. So the product of terms is equal to 1. And similarly, h of n comma 1, right, here you sum over 1 less than or equal to a1, etc. It goes all the way a n minus 1. It has to be less than or equal to k, which is equal to 1. So k is 1, and then you multiply a1 all the way up to a n minus 1, and then you get 1, because there is only one such increasing sequence. So, and that's basically, that's the end of the proof. because of the argument I explained that the whole table can be computed row by row in each case. So we are done basically by induction. Done by induction on n. And yeah, so that's a nice property. I mean, it's a crazy thing to me that the formula is so simple. But this formula is also, if I wanted you to actually compute the number, you would have to run over all increasing sequences like this. That may take a while. Computationally, there's exponentially many of those, right? Yeah, so you want a better formula. And but while I'm here, let me also mention another nice interpretation of these Stirling numbers, for that you need a little bit of linear algebra, but not too much. So let me remind you that we have these following factorials, which is so it's brackets x sub k is just x times x minus 1 times etc. times x minus k plus 1. So yeah, previously I defined it that's like the number of injections. So if x is an integer, if x is a positive integer, then bracket x sub k is the number of injections from bracket k into bracket x. So, but this formula can be defined for this formula here can be defined for any real number x, right? It's just a polynomial in x of degree k. So what I'm gonna explain right now is that first of all, if you consider just the monomials 1x, x squared, all the way up to x to the n, these form a basis of the space of degree n polynomials. Right? I mean, that's very easy to see. But what is also true is that 1x sub 1, anyways, I guess 1x sub 1, x sub 2, etc., x bracket x sub n also form a basis. So these are, you just think of a vector space. You have a vector space, you have one basis, and then you have another basis, which I haven't even explained why this is a basis, but it turns out to be a basis, as I'm going to now explain. So the claim that I'm going to make is that whenever you have two bases, you can form a transform matrix, right? You can express the elements of one basis in terms of the elements of the other basis, and vice versa. So what is the matrix which takes this basis to this basis? And it turns out that that matrix is precisely the matrix of Stirling numbers. So yeah, here is the result. Which again, so for now you can forget all I said and just think about it's some identity involving the Stirling numbers, which I also think is kind of cool. It's very clean statement. For all real numbers x and all integers n, greater or equal to 1, if you can expand x to the n, right? So the point is that I want to expand x to the n in terms of the basis of the following factorials. And the coefficients are going to be literally the Stirling numbers of the second kind, bracket x to the k. So yeah, maybe I should try an example. Should I try an example? Yeah, let's try an example. So let's say I take my picture again. So I should choose some suitable row. Maybe I should choose 1, 3, 1. So yeah, and I also have to include 0. So 0, 1, 3, 1 is going to be my coefficients here. And okay, n is equal to 3, so x cubed is equal to 0. Well, 0 times 1 plus, because x, yeah, the first one of these is going to be just 1. 0 times 1 plus 1 times x1 plus 3 times x2 plus 1 times x3. Which is, okay, this is interesting. All right. So let's see if I can compute. Oops, it is supposed to be x3. So all right, this is 0, and the next one is just x plus 3 times x minus 1 plus x minus 1, x minus 2. X plus 3x squared minus 3x plus, what is it, x cubed minus 3x squared plus 2x. Is that the... so let's see what's going to happen. So 3x squared is going to cancel out. And then x minus 3x plus 2x is going to cancel out, and what I'm going to get is just x cubed. Which, okay, so that's another, it's pretty crazy, right? You're taking two natural collections of polynomials, and then you immediately get out these Stirling numbers as just the coefficients. So yeah, I have the matrices. So yeah, so the matrix literally, if you fix some capital N, then the matrix is gonna basically, it's gonna be some lower triangular matrix, which has zeros above the diagonal. So this is the matrix of going from 1x all the way up to x to the n to 1x sub 1 all the way up to x following factorial. Okay. Now, so how do I prove this theorem? And the proof is, well, it's another trick. Right? So, okay, should I copy again what I'm about to do? Let's copy the theorem. So the proof is, first I'm going to start by proving it for all. I'm going to start by proving it. So first I'm going to assume that x is an integer. X is a positive integer. So here, the statement is for all real numbers, but first I'm going to prove it for positive integers. And then what I'm going to do is that I'm going to find a combinatorial interpretation on the left-hand side, which is extremely easy. X to the n is the number, it's the number of basically all sequences of all, yeah, let's say words of length n in the alphabet bracket x. So you just take letters between 1 and x, and then you just find all possible words. So that's the left-hand side, and the goal is to interpret the right-hand side to show that the right-hand side counts the same objects. So how do we interpret the right-hand side? Maybe should I try some word? Maybe let me try. Let's say, for example, let's say x is equal to 3, and then my word is something like 1, 1, 3, 2, 3, 1, 2, 1, 1, 1, 2, 3, 1. So n is whatever the 3. N is 13. Then if I just label these positions, then each letter is going to give me a set. Right, if I just number all positions 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, then I can record positions of 1. Positions of 1s are going to be a set 1, 2, 6, 8, 9, 10, 13. And positions of 2s are going to be 4, 7, 11. And positions of 3s are going to be 3, 5, 12. Okay, so and this thing here is a set partition. Right. If I just take this set, this is a set partition. It's a partition of bracket n into how many blocks? Into x. Well, if all blocks are non-empty, then it's going to be x blocks. But in general, some of the blocks are going to be empty. Right. So, well, in this case, into x blocks. If all letters were used. And so in general, if you look at this summation, then it's a summation over k. So k is going to be the number of letters used. Let k be the number of letters used in our word. So I'm going to start with some word like this. It could be a word of all, which just consists of all 2s, just 2, 2, 2, 2, 2, 2. And then I wouldn't get an honest set partition, because I would have just one set. I would have only one block. So, and the letters could be arbitrary, but still recording the positions of each letter gives us a set, gives us a partition of bracket n into k blocks. Right, so maybe I should yeah, so you have, whenever we have a word, then it gives you a set partition into some number of blocks. But then if I only show you the partition, then because the order of sets in the partition doesn't matter, you don't really know which letters which letter was assigned to each partition. So this is not a bijection, right? This is the information. As you replace a word by a set partition, you lose some information, and so it's like a D to 1 map for some D. And so what is this D? Well, the claim is that we get an X. You have this following factorial to 1 map for each fixed K, right? Because you have to assign different letters to different blocks. And there's X options for block. So you order the blocks in some way, and then you have X options for choosing a letter or assigning a letter to the first block, and then the second block has n x minus 1 options for block number 2, and etc. X minus k plus 1 options. Yeah, basically you have to choose an injection from the set of blocks into the set of letters. Block number k. And therefore, by the addition principle, right, so for each k, thus for each k, the number of words which use exactly k letters, k different letters, is S of n comma k, that's the number of set partitions you can get, times this following factorial. And as you sum over all k, by the addition principle, you get x to the n. So this finishes the proof in the case when x is a positive integer, right? But we claimed it for all real x's. So how do you get the rest? Well, the idea is that the claim for x, for arbitrary x, follows for the following reason. You have this formula, right? Let me copy the formula again. So the claim follows since both sides of this formula are polynomials in X. These are polynomials, and we showed they agree at infinitely many values of X. So if you have two polynomials which agree at infinitely many values, then they have to have the same coefficients, as they have to be equal as polynomials, because their difference cannot have infinitely many roots. It can only have at most the degree, or at most n roots. But we found infinitely many roots, so the difference has to be a zero polynomial. So, and since they are the same polynomial, they have the same values for all real x's. Yeah. So that's the proof of, again, I think this is a very beautiful result. And the proof again is, the new trick you learn in this proof is that if you want to show something for arbitrary real numbers, if you're dealing with polynomials, then you can only restrict to the integers, in which case you can use the familiar tools of, the familiar tool that we always used is that we interpret the right and left hand sides combinatorially and then find a bijection. And now you can prove real number identities using that technique. Okay, now let me continue trying to come up with the formula. So let's see. So far we have the recurrence relation. The recurrence relation tells me, let's say you want to compute this this number here, n equals to 9 and k equals to 4. Well, okay, it's using the recurrence. You can compute this number. You can compute this number if you know these two numbers in the triangle, and for that you need to compute the 3 numbers here, and then 4 numbers here, and then so basically, in order to compute just one number, you have to compute this whole parallelogram of numbers, right? Which I mean, it's nice, but what would be even nicer if you only well, I mean, it's, how do I phrase it? If you had to write a program, then your program would have to compute a lot of numbers. I mean, that's just true. But so let me try to write basically the same recurrence, but in a slightly more convenient way. So the program you're gonna write is gonna be slightly better, I guess, in some sense. So yeah. Anyway, so here's another statement about Stirling numbers. Which is that s of n plus 1, comma k is equal to the sum for I from 0 to n, and choose I s of n minus I, comma k minus 1. Right. So the cool thing about this formula is that right, so k is here, and I can basically, the improvement is that I get rid of the column above my number. Right? So I'm only using the s n plus 1 comma k, and here, so the catch is that in this recurrence, this is always k minus 1. So in other words, this recurrence allows you to compute not row by row, but instead you compute just like column by column. So you first can compute k equals to 1, then using that you can compute k equals to 2, and then etc. So yeah, I mean, that's a different kind of recurrence. So let me try to, again, the proof is going to be similar to what we usually do, is that we find a bijection between the left and the right hand side. So for the left hand side it's very easy. It's just by definition s of n plus 1 comma k counts partitions of bracket n plus 1 into k blocks. Yeah, and for the previous recurrence we looked at the block which contains n plus 1. But what you can also do is you can you can kind of remove, previously we removed n plus 1 and we got some fewer blocks, but what you can also do is you can just choose the block for n plus 1. Choose, so first of all, let's, whenever you have such a block, then you can let I plus 1 be the size of the block which containing n plus 1. Right, and so if the size is I plus 1, then one of the elements is n plus 1, and the rest I, you get to choose whichever ones you want. Choose the rest I elements of this block in n choose I ways. And that's basically it. Right? We have chosen one block, but then there is also, we have to choose another k-1 blocks. Choose the remaining blocks. So for the remaining blocks we have n-1 and n-I elements. In S of n-I, and then the number of blocks is k-1, so in this many ways. And that's where you get this formula from. And okay, so this is kind of, this is not teaching us any new tricks, but then I'm going to use a similar technique to give you a recurrence about some other kind of nice numbers, which is, so analogously to what we previously did. Previously we looked at like compositions into a fixed number of parts and then compositions into arbitrary number of parts. And here, so far I've been talking about set partitions into a fixed number of parts, but now let me talk about partitions into arbitrary number of parts. And these are counted by Bell numbers. So the Bell numbers, just by definition they're defined. B of n is just the sum k from 0 to n s of n comma k. So let me try to give you a table. Right, so it's just you vary k, so you look at all set partitions of bracket n, and you still disregard the order of the sets. So here is the table. We set b of 0 and b of 1 to be equal to 1, and then the table basically looks like this. So the connection with the previous table is that it records the row sums. So, oops. Here the row sum is 2, and then it's 5, and the next one is 15. So 2, 5, 15, and the next one is hopefully 52. Right? Yeah, 52. And etc. So again, the Bell numbers are just as Stirling numbers. It's hard to give a direct formula, but let me, similarly to the recurrence I had here, let me try to give a similar recurrence for the Bell numbers. So here's a proposition. You can compare it to the proposition I had for the Stirling numbers, and it looks literally the same, right? Except that there is no k anymore. So b of n plus 1 is equal to the sum, or I from 0 to n, of n choose I times b of I. So I mean, this is a very nice recurrence. You can compute the next number in terms of the previous ones, and the coefficients are just the binomial coefficients. So should I try an example? Let me try an example. So let's say n is equal to 4. Is that all right? Yeah, let's say 4. So b of n plus 1, which is b of 5, which we know from the table is 52, should be equal to, I'm taking n choose, so 4 choose 0, 4 choose 1. Okay, so it's 4 choose 0. 4 choose 0, b of 0, plus, etc., plus 4 choose 4 times b of 4. Okay, 4 choose 0 is 1. 1 times b of 0, that's 1. 4 choose 1 is 4 times b of 1, that's 1. 4 choose 2 is 6, times b of 2, that's 2. 4 choose 3 is 4, b of 3 is 5, and 4 choose 4 is 1, times b of 4, that's 15. So the answer is 1 plus 4 plus 12 plus 20 plus 15. Uh, 52. Yeah, that's correct. That is 52. Okay, so how do I prove the proposition? And the proof is really just the same idea without the case, right? You choose the block. Choose the block of size I plus 1 containing n plus 1. You can do this in n choose I ways. There has to be exactly one block which contains n plus 1. And the rest of the blocks give you a set partition of n minus I. Wait, is there? Yeah, I guess. So n choose I. Yeah, I guess there is a subtlety here. N choose I is equal to n choose n minus I. So choose the rest. The rest is going to be a partition of n minus I in b of n minus I ways. So the actual formula you get is b of n plus 1 is equal to the sum of n choose I times b of n minus I. But that's the same as n choose n minus I, b of n minus I, which if you now replace n minus I by some new variable, then you get this formula here. So that's the proof. Which, yeah, so by the way, I wanted to mention, since I have a few minutes left, I wanted to mention that's not going to be checked on any midterms, and it's not in the notes, but it's a cool algorithm. So let's say you forget these Bell numbers. Of course, you can compute them using this recurrence, but here's a graphical way to compute. So that's a detour, and that's called the Bell triangle. So how to compute these Bell numbers using a Pascal-like triangle? So here's the idea, and I'm just gonna compute. So you start with a single one, and then each time I'm gonna create a triangle, which I'm gonna construct row by row. And each time I'm gonna take the last number in my row, and I'm gonna copy it into the first number of the next row. So yeah, the number here is gonna go into this row, and the number here is gonna be copied into this row, and etc. So I copied the 1 and I put it here. And then I'm gonna, to construct the rest of the row, I'm just gonna take these, each number is gonna be the sum of the number to the left and the number to the top left. So I sum up these two numbers, I take the sum of 1 and 1, and I get a 2. And then I copy the 2 into the next row. So 1 plus 2 is gonna be 3, 2 plus 3 is going to be 5. So whenever I see this number at the end of the row, I copy it. 2 plus 5 is 7. 7 plus 3 is 10. 10 plus 5 is 15. And then I copy 15. 15 plus 5 is 20. 20 plus 7 is 27. Then I get 37. And finally, 37 plus 15 is 52. So you see that I'm getting these numbers here are the Bell numbers on the diagonal. So it's a cool, simple way to just, if you want to remember the numbers, then that's the triangle you get. And you may wonder, like, what are these what is the combinatorial interpretation of these numbers? And that's actually slightly complicated. You can Google it. Just Google Bell triangle, and then you're going to see some combinatorial interpretations. But that's actually not entirely natural objects. But you get these Bell numbers on the diagonal. The n on the diagonal. Yeah. Okay, I am out of time, so I will see you all on Wednesday. Have a nice weekend, everybody, and see ya.